Hello everyone, my name is Miao. Together with my teammates Tamami, Mingyan, and Gray, we will share with you our project with Chicago Metropolitan Agency for Planning, where we use deep learning algorithm to expand stormwater infrastructure data and build climate resilience. I would like to start out by explaining why this project is important. Our project is part of the effort to enhance the city's ability to respond to the climate change. According to the National Climate Assessment in 2014, the Midwest is at risk of negative impact from climate change. In particular, increased precipitation and flooding will put pressure on existing infrastructure, leading to flood damages and reduced water quality and availability. To address this problem, we are honored to collaborate with Chicago Metropolitan Agency for Planning, who is in charge of the watershed monitoring in northeastern Illinois. Together, we aim at solving the following big-picture questions. What type of stormwater storage infrastructure are required to mitigate flood risk, and where are the opportunities to improve or extend existing stormwater infrastructure?
More specifically, our primary goal is to develop a comprehensive inventory of stormwater storage infrastructures. By doing so, we can provide city planners and other stakeholders with a valuable resource for addressing climate change. As illustrated by the map of Illinois in the bottom left, the existing stormwater infrastructure dataset reflects infrastructure in only 2 counties, which are represented in red. This narrow coverage is insufficient for effective planning across Illinois. To address this limitation, we will use deep learning techniques to expand this dataset to include other counties. For the final deliverable, we will develop a deep learning model that can accurately identify stormwater storage infrastructures and their types. As shown in the images below, the model will process satellite images and output predictions that identify and classify different basin types, such as ponds and wetlands, which are essential components of the stormwater management system.
Next, we'll be talking about the model development work we completed this quarter. Our model identifies different stormwater infrastructure by categorizing each pixel in an input image into a class, such as ponds or wetlands. The goal of our model was to maximize the intersection over union. The intersection over union is a measure of accuracy that is defined as the overlap between the model's predictions and the labeled area. The highest IOU that can be achieved is 1, which indicates perfect overlap between the predictions and labels. The products of work completed last quarter were the materials for the work we did this quarter. From last quarter, we had shape data maps, which identified the labeled areas where the stormwater infrastructure were located, aerial images for the relevant area of infrastructure detection, and an initial deep learning model implementation. The highest IOU achieved last quarter was approximately 0.55.
Based on last quarter's great work, we made significant progress this quarter. First, we identified and addressed problems with the existing model by enhancing the training pipeline and adopting a more robust sampling method. Second, we streamlined our model optimization process by automating the tuning of model settings and evaluation for improved training efficiency. Furthermore, we are halfway through incorporating new data sources, including those on rivers and elevation. One of the key contributions we made was improving our training pipeline. Previously, adding a new type of basin for the model to identify required starting over and performing extensive preprocessing to convert data formats. To streamline this, we implemented a new approach that converts data format on the fly and allows for a more flexible configuration of basin types during the training process. Another issue was about some areas in our training data where labels were missing, leading to inaccurate predictions. To address this, we developed a new sampling method that focuses on only the labeled areas while still maintaining exposure to the context around the labels. This improves the quality of our training data and enhances the model's accuracy.
Another improvement is that we have automated the model optimization and evaluation process. Our model has numerous settings such as the intensity and probability of filters applied on images and the learning rate. To optimize the model, we have incorporated an industrial standard automatic tuning module. We specify a range of values for the settings we wish to experiment with, and the tuning module trains the model and predicts the value most likely to improve the accuracy. It then repeats the process with the new settings, running multiple training in parallel to reduce tuning time. In this experiment, we specified 3 settings and set value ranges for each of them. On the right, we can see the result corresponding to different combination of setting values, ranging from 0.46 to a bit higher than 0.66. This can help us identify the optimal parameter values for our model. We have also enhanced the evaluation method by conducting multiple training trials, each with randomly split train and test dataset. The model's performance will be assessed using the mean and standard deviation of the test result from these trials. This approach helps to avoid selecting a model that performs well on a specific dataset by chance.
So here's our model performance for this quarter. The highest intersection of union we achieved is 0.68, which is 24% improvement from last quarter. This demonstrates significant progress in the model's accuracy and performance. As we could see in images, the model are able to differentiate pound as labeled in the orange color and wetlands as labeled in the green color with accurate segmentation shape. Even though we have made such improvement, there are a few issues with our current model. First, the model confused related objects, such as rivers and ponds, due to their visual similarity, which impact its accuracy in distinguishing between these features in error images. The model also struggles to detect infrastructure that lacks clear identifier, such as dry bottom detention basin, because these features often blend into surrounding environment, making them difficult to discern. Our proposed solution is incorporating river network and elevation data, which will be explained in the later slides. As illustrated in the above picture, one of the frequent mistakes the model made is that it confused the river with the ponds. Without the ground truth label, the model fails to recognize the difference between a river and a pond.
Another major issue with the model is that the model has difficulty detecting infrastructure not readily identifiable in the aerial images, like dry bottom detention basin. As you can see in the figure on the top of the slide, the model is not able to identify the dry bottom detention basin in the sample area. In the bottom figure, the model incorrectly detects dry bottom mesic prairie detention basin.
Next, we'll be discussing the ongoing enhancement and future work. As discussed above, we propose adding a new dataset to our training model. By incorporating river-shaped data into the ground truth, we allow the model to differentiate between river and ponds, which improve its detention ability regarding various water bodies.
Elevation data is readily available for all of Illinois. By incorporating this elevation data, we can provide the model with additional context to improve differentiation of classes. The elevation data would inform the model that low-lying areas near water bodies are likely to contain stormwater infrastructure, and that areas with higher elevation are less likely to contain certain types of stormwater infrastructure. Moreover, the model would be able to pick up the patterns in elevation, where elevation changes indicate boundaries between land use types. Overall, we believe the incorporation of elevation data will contribute to significant improvements in model accuracy.
In our latest update, we intend to add both river and elevation data to enhance our prediction accuracy. Currently, we build scripts for extracting and incorporating river and elevation data into the model. We are still in our developing phase, and we want to ensure the model performs reliably with the new datasets. Our next step will be to evaluate how this new data is being incorporated, and how does it influence the model's ability to differentiate between classes. Finally, we plan to conduct testing to verify the improvements in the model accuracy and robustness.
We developed a strong foundation for further improvements for the model. Our work can be further improved by enhancing the data, which would involve completing and verifying the incorporation of river and elevation data, and collecting data across different seasons and geographies. Some future next steps for the project include creating a comprehensive validation dataset and investigating the feasibility of predicting other classes which have lower data counts. By implementing our suggestions, we believe that the model performance can be further improved. We are excited for the progress of this project and look forward to seeing the future impact of our work. That concludes the presentation for the CMAP team. Thank you for your attention.